right. Hi, everybody. Welcome to our live stream, Let's CTF. Today, I'm going to be walking through a Capture the Flag challenge having to do with software reverse engineering. This is a challenge that was written for a conference that we helped develop some challenges for here at Neuvik, and it is fairly straightforward in its process. So we're going to get familiar with a couple of different tools, take a look at some kind of built-in things that we can do in Windows, and then really dive into reverse engineering in a disassembler. I'm going to be using IDA Pro, but you could do the same things that I'm going to be doing in IDA Pro inside of any other disassembler. Things like Binary Ninja or Gahidra would work for this just as well. The goal here is to just kind of give a taste of what reverse engineering in a CTF might look like, and also a little bit of knowledge about things like the Windows API. This is a Windows-focused challenge. It's a Windows executable, a PE file, and we're going to be taking a look at how it does what it does. Feel free, if you are in the chat, either on LinkedIn or YouTube, to throw questions out, and I'll be taking a look at those as we go along and try to answer them to the best of my ability. We've set aside an hour for this. It may take anywhere from 30 to 60 minutes, depending on the number of questions we get and how in-depth we go on a couple of the individual items. With all of that out of the way and no further ado, let's go ahead and jump over into my virtual machine over here. My virtual machine, I have open a folder that has the original flag that was used to create the thing we're decoding and an encryption challenge that we're going to be dealing with. And that's why we called this instance Decoding Dilemma. We have a encoded file of some kind, and we want to get the flag back out of this. For a proof of concept, just to kind of show what it looks like, I did go ahead and leave the plain text flag file up here. We can see that, and that's okay. I'm not going to open it until a little bit later as proof that we were successful. Instead, I'm going to be focusing in on this file that is the encoded version. Now, this particular CTF challenge did come with some instructions. And in the instructions for the challenge, it said that we had intercepted an encrypted file that had some kind of secret in it, and we wanted to be able to decode that or unencrypt that to get that information back. Fairly straightforward, common capture the flag pretense to give you something to work with. And then alongside that, we also have the file used to create that encrypted thing. There are a number of strategies that we might use to start taking a look at this. We could just try to run it and see what happens. If we do that, we're very quickly going to see if we kind of hide this flag file from it. Let's create a new directory to throw that in just for a moment. If we are to hide this flag file, which it turns out this executable is going to be looking for, and we do kind of pop up a command prompt here just to run the thing and see its output. Here we go. There we go. If we run this, it's going to say it failed to open the flag file. Running a sample like this in a reverse engineering category in a CTF is not an uncommon thing to do as a first step. Unfortunately, it just didn't get us anywhere this time. There are some other kind of static approaches we can take rather than this dynamic approach of running the application. And there are some dynamic approaches we could take as well, like attaching a debugger. Because this was in a reverse engineering category and not a pointables category, not an exploitation-focused category, I'm going to go and take those static methodologies to start with. And that's, again, in part because it gives us an opportunity to show the skills that might be used in a capture the flag. So hopefully that's exciting for all of you. I'm going to go ahead and dive right in. The first thing we could do is use a tool called strings, which just looks at the executable for anything that has a certain number of consecutive bytes in it that looks like text. And that's configurable a little bit between ASCII text and Unicode text. It's configurable in the length that you want to look at. Because I wrote this challenge, I happen to know that that's not going to be successful. So I'm going to skip that particular static check, only because I already know that. If I was doing this in a real competition, I would absolutely do things like look at the strings that are inside of it. My approach instead is going to be taking a look at the actual code that is inside of this executable. A portable executable file, which is just the file format used on Windows for things like EXEs and DLLs, has headers, and then it has a section in it that is executable code. All of that can be exposed to you via disassemblers. There are also some other tools that can be used to look at it. I'm going to dive right into the disassembly methodology. To do that, like I said, I'm going to be using IDA Pro. And when you first start up IDA, you kind of have this window here. You could either click New, you can click on Go. Go is just going to open an empty IDA window. New is going to have you pick a file that you want to disassemble. I usually, just out of habit, click Go, and then I drag my executable in. You can do that, or you can click New and then select it. I'm going to select this encryption challenge. I'm just going to pull that into IDA here, and it's going to start doing its analysis. The first thing it does is ask me about the file that we're looking at, and it makes a guess about its format based on the headers. In this case, it is a portable executable file for a 64-bit Windows system, and it was able to detect that. So I'm going to go ahead and let it use its decoding, its disassembly for that particular file format. It makes that determination by looking at some magic numbers in the header. All portable executable files start with the characters MZ, and then they have some other information in them that tell us that this is a Windows executable. That's part of the COF file format that was inherited by the portable executable file format. Since this is a portable executable, I will go ahead and click OK, let it do its automated analysis, and it tells me this was created with a PDB, debug symbol information. I could tell it, go ahead and try and find that, but I know it won't succeed because I deleted that file. It no longer exists on my system. So I'll click No and just kind of move on. There are a couple of other pop-ups here that aren't relevant to what we're doing and are side effects of the way that I compiled this. Now that we've let it have a few seconds to do its automated analysis, we can see up here at the top that we have kind of a pictorial or color-coded view of this file and the different regions in it. And those different colors mean different things. For those of you who are colorblind or otherwise can't tell, this first color here is a light blue. It's kind of a cyan. The second one is a darker blue. Next, we have brown, gray, tan, pink, and green. In this system up here, in this image, we can see that there's a lot of areas that are regular functions. That's kind of blue here. There are some sections that are library functions. Those are determined by IDA by taking a look at what code is there and if it matches any patterns that IDA is aware of. And then there's also some sections here that are marked as external symbols. Those are things that are imported from other libraries, other DLLs, that sort of thing. And then there is some unexplored space here. IDA is going to use kind of path analysis and graph edge analysis to determine what it thinks is code and what it thinks is maybe not code or might be data. In this case, these kind of tan areas, IDA didn't see anything that called into that or returned to those addresses, so it didn't treat it as code, and that's fine. If it turns out that it is code, there are some key bindings or some functions we can use inside of the tool to determine, yes, this is code, let's treat it as such and decode it. That's very common to see in things like malware that might be hiding where its execution is and unpacking that at execution time. But this is just a normal compiled executable for Windows. So this might be dead code, but more likely it's just something that's unexplored that IDA didn't feel it needed to take a look at. Because we did load this in IDA, the first thing it's going to do is take a look and try to find the program entry point. The program entry point is the first thing that's going to be executed when you start this program. And because this was compiled with the C runtime, it is a C executable, IDA found the main function, and it did that by first starting at the C runtime entry point and following that through to main. That's going to be the case when you open most C or C++ executables. It's going to find that main function that was declared. In a DLL, it's going to find DLL main, but both of those are just marked as a part of the C runtime header and the PE header as where the program starts. So when I just ran this program in my command line, this is the code that was executed. Inside of this, down here on the bottom left, we can see a graph view, which is a view of the current function that we're inside it. This is what main looks like from an assembly perspective. And we can see that it has a bunch of small boxes here. Those are what we call basic blocks. They are contiguous sections of execution that will always run together. We have a big one up here at the top where it's doing things like initializing variables and calling functions. And then after that, we can see it's making some kind of decision here. And that's where we get this first set of branching. It either comes down to the left or it comes over here to the right based on the result of this jump if not zero or jump if not equal instruction. Now, at this point, we have a couple of options. We can, because modern versions of IDA, including IDA-free, ship with a decompiler, try to view this as decompiled C code, something that would represent the actual code that generated this assembly. And so if I hit F5, we get that view. This is not always going to be possible, but this is a great way to tackle problems like this very quickly. Because my goal in this particular demonstration is to actually show what this looks like from an assembly perspective. I'm not going to look at this window. But just taking a look at it quickly, as you are doing, we can see that a bunch of errors that we kind of saw are there. For example, failed to read from file. We saw that when we tried to run it, and some other things there. We can see that in the disassembly view as well, if we kind of move down to some of these other blocks. When we have a branch like this, we can see a green path here and a red path. Green means true, whatever that decision was, and red means false. And so false is often going to be an error case. And if I double click on that line, we see here that print, failed to open flag file. The thing that we saw when we ran it, well, it turns out that that was one of those error cases from this first basic block in main. When we're looking at the top of a function, there are some sections or chunks here that we can be aware of that are common patterns. And the first one that we see is these first three instructions here: push EBP, move EBP ESP, sub ESP30. That's setting up the space on the stack for locals, and it also tells us we're using a stack base pointer. If you're familiar with base pointers in assembly or as a construct, this is what they're going to look like typically in many executables. We can also see that we are using 32-bit addresses here, so it looks like this was compiled as a 32-bit executable, not a 64-bit executable. So that's running inside of something called Windows on Windows, which is a 32-bit emulation that Windows uses for 32-bit systems when it is running in a 64-bit mode. Next, we have some initialization. This is setting up our local variables. So there are a bunch of local variables that were declared, and those are being initialized here. The first one that we can kind of see is that we got that base pointer, and then we're XORing that with something and storing that. That happens to be a security feature called a stack cookie or a stack canary. So I can click on this and give that a quick name, and I'm just going to call that v_stack cookie. So if I see it somewhere else, I know that that's all that is. It's not something that I need to be aware of as a local. It's one of those security features. Then I have some other names here. I automatically called this size, it called this H file, this LP buffer, and that's because it's deriving that information from functions that we're calling. It takes the functions that it's aware of from the Windows API, and it will automatically name things like local variables for you. Very often that's useful. Every once in a while, a variable might be reused, and that ends up giving us a false sense of what that thing is. In this case, those are probably accurate because this is a fairly small function, and thus it's not doing very many things at once. Now we have a few options. We already did see that there are some error cases. This is doing error checking. It has prints. We can look at those strings in IDA in the same way we could have with a command line tool to take a look at clues to the behavior of this application. We can also look at interesting functions from our imports and say, where is this opening files? Where is this taking inputs? And try to determine its behavior based on those functions that are being called. Or we could just start at the top of main and go down. When I'm doing exploit development or vulnerability research, most of the time I'm going to be looking at those functions first, because I'm interested in user input and how that might influence the application. But because that's not my goal, I'm not trying to exploit this, I'm just trying to determine its behavior, I'm going to start at the top of the function and work my way down. In this first basic block at the beginning, as we kind of pointed out, we have a bunch of setup that calls initially to create our local variables. We have a call here to some kind of subroutine, and it's pushing a 0. And then we're calling srand, another function call, followed by rand. So we're initializing a random number of some kind here. Then we are calling create file, pushing a whole bunch of arguments to it. All of these pushes immediately before it are the arguments to create file. And if I didn't know what that looked like, my first place to look would be MSDN. MSDN is the Microsoft Developer Network documentation. So I could open up my browser, or if I had something like Visual Studio installed, and Google or Bing or DuckDuckGo, whatever that function is. In this case, because srand and rand on Windows follow the POSIX standard, I know what arguments those are taking. We're taking a seed here, and then that is seeding the random number. And then for rand, it's just going to give us back a number. One of the things to be aware of in Windows, and in fact in almost all operating systems, is that when we make a call, we expect the result of the function we're calling to be in our A register. That's going to be EAX, RAX, or one of the sub-registers. In this case, we see that we're moving something out of AL, that is the low 8 bits of that 32-bit register, into something called buffer. But because that's the return from rand, we know that at least at this point, it's a random number. And there are a few ways that I can make a note to myself. In this case, I'm going to hit the colon key and enter a comment. This is a random number. That way, if I look back at this function later, I know that we're storing a random number here into buffer. We're not using it immediately. We're just taking that as a result of rand. I can look at cross-references to this variable by hitting the X key, and I can see that here inside of main, it is used a bunch of times. First, we store this random number. Here we're doing a load effective address, so we're getting the address of that random number, moving that into ECX at some point, and then we're also looking at this variable again later as a buffer. We're looking at offsets into it. So it's likely that this is one of those cases where some space on the stack is being used for more than one local variable. It's just reusing that because it determined that after a certain point in the function, the random number is never used again. So it's safe to overwrite that value with something else. And that's not an uncommon behavior to see in assembly because it wants to optimize the amount of space it's using. So far we know that before this point, we are doing some initialization and we're creating a random number. I'm going to add a posterior line comment that's just shift insert and say, we've generated a random number. That's all we've done so far. The next thing that we do, we can see here, is that we are calling create file. And as I mentioned, we can look up the arguments that takes and kind of determine why they're being sent, what they might mean from the MSDN. This is the kind of first step I would take for a function I wasn't aware of. Look up what arguments it takes, what is it expecting to do, and what it returns, because it's going to be performing some behavior and returning some kind of value. It looks like it's being a little slow on my internet here. There we go. So we can see that as arguments, it's taking a file name as its very first argument, the type of access we want, something called a share mode, some security attributes, creation disposition, flags, and then a template file, which is optional. Going back over to our disassembler, we can see that several of these are null. Our share mode is 0, our security attributes are marked as 0, there's no template file, flags and attributes are 80. We can determine what that means by using some standard symbolic constants. In this case, we can click on, for example, that number 80. I right-clicked on it, and I can use standard symbolic constant. We're trying to find out the flags and attributes and maybe the creation disposition to figure out how this file is being opened. From my experience, I know looking at these what that is, but let's just kind of take this 3 as an example. I'm going to use a standard symbolic constant, and this opens up a list of known constant things that have this value of 0. And it turns out that there are a lot of them of different types. All of these are coming from the Microsoft SDK. In order to narrow down which one it is, we could take a look at our parameters here in the MSDN and take a look at like maybe what this desired access mask might be. It's going to be some constant called something like generic read or generic write. So if I just start looking at that, I can see if there's anything that kind of matches that. Eventually we'll come along with our creation disposition. Here we go. Where are we? There we go. That's share mode, security attributes. There we go. And even in the documentation here, we can see a creation disposition of 3 means open existing. So I can come back in here and I can, again, use that standard symbolic constant for open existing. And now when I click OK, it's just going to label that for me. So it's a little bit easier to kind of read what that is. So we're opening some kind of existing file, and the file name is flag.txt. It makes sense that that's the thing that it's trying to open for reading. Then it's going to take that return value here, which is in EAX, and it's storing that in something called hfile, because looking at our documentation, the return value here is a handle to the file. Handles are an opaque structure on Windows that say this represents something from our file system or some other type that Windows doesn't necessarily want us to have the internal knowledge of, but that we can pass to other functions. For example, the very next thing that it does is it calls getFileSize, passing in that file handle as an argument. So now we know that they're opening a file called flag, and they're taking a look to see how big that file is, and then comparing that file size with 400 hex. And if it's below or equal, so if it is less than or equal, we're going to do some more things. And if not, it prints out an error. It's going to say that the file is too large because they don't want to have to create a whole bunch of memory or a new file based on that. But assuming that the file is not too large, then we see that they're calling malloc, which is a C function to allocate memory. And as the argument, we're passing in the size. So again, all we're doing here is starting at the top of the function and moving our way down to see what are they doing with their inputs that might generate the output that we have that is of interest. Another approach that we could have taken, as I said, there are lots of different ways to solve things like this, is that we were given something called enc.text. It's possible that that came from this particular executable, that it gave us something called that. And in fact, if we look down, we can see that that string does exist, and it's being passed to another create file call. We can do that by moving through our basic blocks here, or we can do view, open subviews, take a look at our strings view here. This is going to find, in the same way that the strings utility did, anything that looks like a set of ASCII characters. And it would, through that process, find this string enc.text, and we could, again, hit X, find cross-references to determine where that is being used. In this case, it's being used in main. We could jump back to this address, and that would allow us to work backwards to see how are they getting to this and what are they writing into that file. I'm going to go back to moving forward, though, from the beginning. So we've gotten the file size of this flag here, and we've called malloc to create a buffer for us to put information into. That buffer, sorry if you can hear the car alarm outside, that buffer is the same size as the file that we just opened. We haven't read the file yet, and we haven't put anything in that buffer. So up to this point, all we've done is open flag.text and allocate memory the same size as its contents. So I'm just making myself a comment to know that that's what we've done so far. Again, I like to use posterior comments for that. That's just shift insert. It puts it on the line after the instruction you're on. Okay. If it fails to allocate, so here we're checking for a 0, which is the same value we're going to see from a null pointer, then it prints out a different error message, failed to allocate buffer. Whoever wrote this challenge actually did error checking as they were going through it. Wonder who that could have been. Now that we have seen that they are allocating space, they're probably going to be using that for something. And so we can cross-reference this variable again, this thing called LP buffer, by hitting X, and see everywhere it's being used. The next place that we see it being, the first place we saw it being used was back up at the top when we were initializing our local variables. It was initialized to null. Here is where we just saw it, and we can tell because of this direction column. Up means higher up in memory, D down means lower in memory, and nothing means the line we're currently on. So we can see that comparison we just talked about, comparing it to null. And then we're reading the value out of that buffer for other places here inside of main. If I was to double click on one of these, that'll take us to that instruction. And it looks like the very next time it's used, it's as an argument, the LP buffer argument, to read file. We know it's that argument because IDA puts that comment there for us, but we can also determine that ourselves, because if this was a custom function rather than an API function, we wouldn't have that knowledge. In that case, we can look at the documentation or reverse engineer the behavior of that read file call to figure it out. But because this is a standard Windows API function, we don't need to do that. We know that it has arguments in a particular order. And if we come back over here to our MSDN, we could find that somewhere down here, scrolling down on the left, we have our read file function. I'll click on that, see our arguments. One thing I'll point out for those of you who are not used to reading assembly on Windows or assembly for calling conventions that push things to the stack, when we are pushing things to the stack, we're doing that in reverse order because of the way the stack is built. Because we want this H file to be closest to our pointer in memory for our stack, it has to be the very last thing we put on our stack. Otherwise, it would be further down. So as we look back, we see that this is pushed in the reverse order that we see here in our documentation. The very first thing is EAX, which we got from moving in from that handle. So we can see that EAX is the same file that we had earlier that we got the size of. The second argument is a buffer. And if we look at our documentation, we can see that that is a pointer to the buffer that receives the data read from that file. So they're opening that file, they're reading it, and they're saving it into this buffer that we just allocated from that malloc function. So read that value in, we have a size, this is the size of the file, because we already know that. We know that that's the maximum amount that we're going to read. And then we have some other value on our stack here being used to represent the number of bytes read. Okay. So after we read that file, we're going to test EAX. This is just a quick way to see, was the return result 0? That's going to be equivalent to the instruction compare EAX 0, but the test instruction is faster. It's doing a bitwise AND operation and seeing the result. So this is just a compiler optimization for an if 0 check. If we get a return value that is invalid, we have an error message, but if not, we call close handle. So we're closing that file we just read, and then we're doing something else. This next block we can see points back to itself. This is what a loop looks like in assembly. Loops might be a single block like this, or it might be multiple blocks. In this case, it's one very small block that is doing something to something. Inside of this, we can determine what its behavior is. And so we see that we have some local variable that's at location 1C on the stack. We're moving 1 byte pointed to by that. This is square brackets means that we're dereferencing a pointer. Then we are taking that value, moving it into var 11. We're adding 1 to var 1C, so that's probably some kind of counter. We're comparing var 11 to 0, and if it's not 0, then we are looping again. So we have some kind of counter that we're using here. And once it reaches 0, we're going to come down here to this next block that we see calling create file and writing that encrypted, that enc.txt, that encoded file. So the encoding is probably happening inside of this loop. We have a file that's not encoded being read in. Then we have some loop occurring. And then we have something here that is doing something else. Now, this is not necessarily doing encoding. We need to take a look at its actual behavior and what else happens between this point here and when we call create file and then write file down here. We can see that this is where they're actually writing the contents to that file. All right, so let's go ahead and take a look. We've closed that input file here, and then we're setting that local variable to something that looks a little weird. It's all F's. It's like a -1. It turns out that that is, if we look at our symbolic constants, a particular constant that is used for files or handles in general called, oops, there we go, invalid file handle or invalid handle value. There we go. And so if we were to set that to that, it just gives us a human readable way of knowing after they're done with the handle, they set it to something that means the handle's invalid. Not strictly speaking necessary, but something that programmers who are kind of savvy on not letting their information leak off of the stack might do, in the same way that we might empty a buffer after we were done with it. We have that buffer. We're going to move that into EDX. EDX is just another register. And then we're going to move that into var 1C. So this was a pointer, and from that, we're copying it into 1C. We're then dereferencing it into EAX. We're adding 1. And then we're also storing that in var 24. So var 24 is some kind of counter or otherwise kind of some value that we're getting from here. Next, we're going to, again, read a value in, read 1 byte of it, move that into a variable, add 1 to it, compare to 0, and then jump if not equal back up to the beginning. This is something that we may want to decode. The other behavior we see here before this create file is a call to subroutine 4010A0. And we see that that's being passed a buffer and a count as well. So it might be doing something inside of that function having to do with that buffer. And then we also see here that we are passing in a single character or something like that to a function. Let's double click and jump into there to see what might be happening. Here we can see that we are once again allocating something. Calloc is going to initialize and allocate at the same time. And we're doing that with a size of, let's see, a number of EAX. So that is the number of bytes we're getting. And it's 1 byte per item. So EAX times 1 gives us the full size that we're allocating. After we've done that, we can see we have another loop here. And this loop is going to be going until our count reaches EDX, and then we're going to return from this function. Before we return, we can see that we're reading out a byte, we're XORing something, and then we're saving that back somewhere else. So here we took in a buffer, we allocated a second buffer of the same size, we're reading a byte out of one and putting it into the other. So we're probably doing our encoding here, not where we previously said it might have been. So instead, when we go back to look at this here, we can determine, well, what is this actually doing? And we see that it is comparing against a 0, and it's going 1 byte at a time through something that's in var1c. Let's take a look at where var1c gets set. We can see that it is set here. var1c is set to whatever EDX is. And EDX had our buffer. And our buffer had the contents of that original file. So this is just another pointer to the same buffer. So I'm going to call this v underscore, let's call this buffer2. It's the same buffer, but it's just in another place. And then we are adding 1 to EAX to look at the second byte of that. We're just moving 1 byte forward. So we take a look at it, we dereference a value, we move that value into var11, we add 1 to this thing that we can see we're now using as a counter of some sort, and then we are comparing the byte that we read to 0. So I'm going to call this v underscore byte read. This is the byte, we're going 1 byte at a time through the contents that we read out of this file. Okay. This, to me, because we're going 1 byte at a time and we are calculating how big it is, this looks like this is probably doing some kind of string length. So we have strlen LP buffer here. This will happen when a compiler wants to optimize a standard call and make it inline. So what this actually is just if we had declared like int inline strcpy, or the compiler decided to do this on its own. So effectively, this is just a string copy. It's not actually encoding anything. It's calculating the size, and it's storing that size back into a byte of a buffer. We get the size of that strling back. So here, when we're moving buffer2 into EAX, and we're passing that to this subroutine, we now know that that first argument is actually going to be the size of that variable, right? So the thing that is calling LP buffer here has that size in it. We are then using that as this count, this first argument, to determine how big of an allocation to make. So we read from the file, we calculated the string length of the thing that we read from the file, and now we're allocating another buffer of that size, +1, because we had that additional 1 that we added previously. Inside of our loop then, that's probably where the encoding is coming from. So we are also passing in, we can see based on our pushes, that buffer value. Inside of this function then, oops, I scrolled up accidentally, there we go. Inside of this function, we know that we're taking in 1 buffer, we're doing something to every byte of it inside of this loop, and we're writing that out to another buffer. So let's take a look at what's actually happening here. First, we are at the top of our loop checking some kind of condition and exiting the loop if that condition has been met. So this tells me that's either a for loop or a while loop. It's not a do while loop. A do while loop is always going to execute once, but here we're checking a condition and exiting the loop prior to doing anything else. So this is probably a while loop, and I'm going to kind of make a comment here that says while something. And we can determine what that condition is by looking at this comparison operation. In this case, we're comparing edx to count. Edx is var4. var4, we can see, is being incremented every time we go through the loop. So var4, I'm going to rename to v underscore loop counter. And I use this naming convention of v underscore just so I don't forget it's a local variable. So we have our loop counter, and we're going until our loop counter and our count, the size that we allocated, are the same. So we're going through one iteration of this loop per byte in the thing that we read in the contents of that file. And then we're going to, inside of the loop, for each of those bytes, we can see that we are starting at the beginning of arg0. And arg0, I'm going to rename to a underscore input buffer. So we start at the beginning of our input buffer. We add to that our loop counter. So if we think about that input buffer as a series of characters that says, for example, flag 1, 2, 3, 4, the first time through, we have a 0. We're going to look at the very beginning of that. The second time, our loop counter is going to be 1. So we're going to start at the beginning here, and then we're going to add 1. So the second time through the loop, we're looking at the L. The third time through the loop, we're taking our input buffer, the beginning of it, and we're adding 2. We're going to be looking at that A. So each iteration through this loop is just looking one further byte into that input buffer. It's reading that out, just a single byte of that. And we can tell that because we have the byte pointer modifier to this move with 0 extension argument. So we're reading 1 byte out of EAX. We're dereferencing that variable. We're reading a byte in the memory it points to into ECX. Then we're moving in arg8. We're XORing ECX and EDX. So EDX from arg8 is something that we're XORing against. So we read a byte, we're XORing it against something, and then we're moving that result into EAX here. We are writing into a buffer that encrypted value, or encoded value in this case. So that tells me, the last thing we have here is we're incrementing that pointer. That tells me this entire loop is an XOR encoder. So while we have not reached the end, while counter is not equal to size, read a byte, XOR that byte, write the byte. Effectively, what we have here is that XOR encoder doing these operations. Read a byte, XOR that byte, write the byte. And we can see that it's always XORing it against EDX, which is arg8 here, which is a static value. We don't know what that static value is, but we know it's not changing. So every byte of this is being XORed against the same number. That means that if we could figure out what that number is, which is itself a single byte, we can decode the encoded information. That doesn't necessarily mean that's all that is in the file. So we might want to take a look at how that file is being written first before we move on. And we saw that back in the previous function. Because we now know that this is taking in a buffer, a count, and some other argument being used as the XOR encoding, I'm going to name that variable to a underscore XOR value. We now have a function prototype up here with variable names. And I'm going to name the function itself XOR encode. If I go back to where it's called, I can now see that we have call XOR encode, and IDA propagated those variable names back for me as well. I can see that here I have an input buffer, I have a count, and I have a comment that says we have an XOR value. That's coming from ECX. ECX came from buffer, and now we can see, well, what value does buffer have? If I hit X for crossref, I can see where was this used last? Where was this last written? And if I kind of here where I don't see up or down, this is the line I'm currently on. And the last time something wrote to buffer, not read from it, but wrote to it, was here. We can see that that's where we had that comment, this is a random number. So we called srand, we called rand, and we saved that random number into this location that is being used as our XOR encoding. So this program is generating a random number and then randomly XORing something. If we don't know what that XOR value is, we could brute force it. We know it's a byte. 1 byte, 8 bits, only has 255 possible outcomes. But I would still have to brute force 255 possible outcomes. I don't really want to do that if I don't have to. So I'm going to see if this is used anywhere else, if there's anything in that output, that encoded file that might give us a hint. Because this is a CTF, it's meant to be solved. It probably gives us the information that we need. And we can see that we do read that value again down here at +1C5. I can jump down to that, see where is that being used. It looks like that is the buffer that's being written to a file. And that H file there is here the result of opening enc.txt. So yes, in fact, that random number that we just saw being used as that XOR encoding is also being written to our output file. To determine where in that file it might be, we do have to analyze behavior. I, from my intuition and kind of knowledge and history and practice, can just look at the assembly and figure that out. But if I didn't have that background, I would want to create some kind of C-like pseudocode that helps me with that. And so here I can take this first call or these sets of calls, and I can write what that C might have looked like. Here we're calling write file. So I'm going to just write some pseudocode here and say we're calling write file. And the first argument we're passing is H file. That H file here is a handle to enc.txt. After the file, we're passing in buffer. And then we have some other things having to do with the number of bytes written, things like that. So we're curious to know, what is this buffer that's being written in this write file call? To make that determination, again, we'll see where was this thing last set? Where was it last used? And the last place that this was used, again, if I hit X, I could see where was this written last. And once again, the last time it was written is still this random number. So the very first thing that this enc.txt is used for is to write the random number to the beginning of it. So if I look at that output file, I should see the first byte is some number, something between 0 and 255. Well, all bytes are between 0 and 255. That's not super useful until this point where I've determined, oh, it's not just some byte, it is specifically the byte used to encode that string. Then we see another write file call here, and this write file is being passed that size of the string that we had earlier, that input, as its number of bytes to write, and it's being passed as its buffer var2c. var2c we can see is being written back up here in this loop. So this is not just doing a strlen, it's actually doing a str copy and counting that at the same time. I'm going to change this comment to a str copy. And I'm going to name that value of buffer2 to be output buffer. So we got the input buffer, we copied that to output buffer, we sent that over into our XOR encode, and now we're writing that, oops, where's my var2c? There it is, I named the wrong thing. And then we're going to go ahead and write that into our enc.txt, right? So, sorry, not create file, down here, there we go. Into this write file, we are writing that buffer, which means, great, okay, we have that buffer in EDX. EDX is being pushed here. So we're writing to that file first a single byte containing a random number, and then we're writing that encoded string. After that, we're closing the handle, and we are returning from main. And if we return from main, that's just going to end the execution of the program. So to go top to bottom, if I wanted to kind of put a comment up here that describes what's happening, I could say open flag file. That's the first thing that happens. Read from flag file. Determine size of flag contents. We forgot create random number. Then we call a function to encode the input, write the random number to enc, write the rest of the encoded string to ENC, and then we return. So that is the total of everything that we're doing in this function, just left as a little comment to us up at the top. Because we now know that, we have a few options. We could write a C program or something like that that does the decode for us, or we could write a Python script. We could also do it by hand if we wanted to. I'm going to go ahead and take that Python route. So I'm going to just open a little Python shell down here, pop that open, and then I'm going to, oops, I opened two of them. I'm going to write up a quick function that takes in a string, that takes in kind of this buffer, and it decodes it for me. So I'm going to start, I have to actually get the contents of this file. So let me do that with open, and then let me grab the path just to kind of get that for me. With open this path, and then the file name is CTF encryption challenge. Nope, that's not what I want. I want ENC, sorry, enc.txt. So I want to read in that file. I want to read it, and I want to read it as binary because that first byte might not be printable. And so I don't want to open it as a kind of human readable file. So it's important to put that B there. I'm going to call that FH, just file handle. And I'm going to say contents equals fh.read. So now I have the contents of that file here inside of a binary string, a byte array or a byte string in Python. I know that my random number is the first byte of that. So I'm going to take contents 0. And then I know that my encoded flag is the rest of it. So I'm going to go from character 1 to the end, and I can see that my encoded flag is everything after that first byte. We can see I had that % as the first byte. It turns out that the random number was human readable. The rest of it is a bunch of bytes that were encoded using that. So I can do something like, loop over each one of those characters, print them out, and get the result. Let me make that just a little bit bigger. There we go. So for car in encoded flag, I'm going to print let's see, first I need to convert it from a character to a number. So I can do that using ord of car XORed with my random number. That's probably going to give me an error because I think I need to ord that too. But let's see what I get. Oh, actually, it's already an integer because it's a byte array. That's right. So let's fix that up. I always have a little bit of an error the first time I write Python in a while, and it's been a while since I've written some Python. So let's see what I get out of this. There we go. So now I have a bunch of numbers, a bunch of integers printed out, and that's not super useful for me. I actually want the characters represented by those numbers, right? So instead, for each character, all right, let's print out the pair, or the character represented by that value in ASCII. And there we go. I can see now this is something human readable. Now, because I used print, it printed everything on a new line. So I can fix that up by, once again, looping through and giving it an end equals empty string. So it's not appending an automatic new line. Oops, I forgot to do there we go. The CHR version of that, end is nothing. Let me actually do that inside of the loop. There we go. This is why live demos always have a problem. Goodness. The live demo gods are not smiling on me today. There we go. And then that is the CHR version. There we go. And now we get something out that has an EU. EOR is always depressed. EOR is another way of saying XOR. It's an exclusive OR operation. This is a human readable thing. It's probably the flag. But because we saved that flag earlier, we can confirm that. Let's go ahead and open up that flag file from the beginning to see what was used to generate that encoded value. And we can see that is, in fact, the contents of the file. We have successfully reverse engineered this executable to get our flag. We go over to CTFD or whatever we're using, and we get our points. Congratulations. We have now successfully completed our first CTF challenge in our Let's CTF series. I hope that you had as much fun as I did. I hope that you learned something from it. If you have a CTF challenge that you'd be interested in seeing a walkthrough for, feel free to send it in. My contact information will be in the comments on YouTube and on LinkedIn. You can also reach out to me on LinkedIn @Tillery. You can reach out to me on Twitter X as @Tillery as well, or you can always shoot me an email, tillery@neuvik.com. for whatever questions, comments, thoughts you might have, or other CTF challenges you think it would be interesting to see walkthroughs for. Our next entry into this Let's CTF series is going to be a packet capture decoding challenge. So I'll start with a packet capture. I'll take a look at that, see what information we can glean from it to then find our flag inside of some network traffic. If you're looking forward to that, make sure that you are following Neuvik on LinkedIn, where we will announce it. We'll also post it over on Twitter or X, whichever you want to call it. When we're going to be doing that, we're going to be doing at least one of these a month for this foreseeable future, and I look forward to seeing all of you then. Thank you for attending if you were here in person or live, and if you're watching this pre-recorded, well, I hope you enjoyed it there too. Thanks, everyone.